When we define the direction field of a first order ordinary differential equation, dy dt equals f of t. Why? The direction field is the field with two entries, and the first component is 1, and the second component is f of t and y. You probably wonder what the reason is to assign the first component to be 1, and here is why. If we have two unknown functions, then we can introduce a system of differential equations. And then, by definition, the direction field of the system is just a vector field with components f and g. And, well, because of the same reasons as the direction field of a single differential equation, the direction field of a system of differential equations is going to be tangent to the parametric curve x of t and y of t. So here is an example. The fat blue curve and the fat red curve are parametric curves x of t and y of t, well, for some particular solutions. And the direction field is just a direction field where the first component is 2y and the second component is minus 3x. Well, and it is possible to convert a single ODE to a system of ODE as follows. We kind of introduce a dummy independent, well, if our ODE is has independent variable x and dependent variable y, then we introduce a new independent variable t, and then we just write that x equals t. Well, I know it sounds silly probably, but then x prime equals 1, but then it means that what we get is that the original single differential equation and non-autonomous single differential equation is equivalent to a system of differential equations which is autonomous. And this by doing this trick, we can change any non-autonomous first order differential equation to a system of two first order differential equations which is autonomous. Well, and basically the concept of the direction field, it belongs to the theory of systems of differential equations rather than single differential equations. And we usually use it to study systems of differential equations. But it can be applied to single differential equations in, well, this simple manner by introducing a dummy variable t and letting x equal t. Okay, so that's the reason. And I also want to give you a kind of an aspect of what's going on when we solve separable differential equations. Is that if we have differential equation that looks like, well, the right hand side looks like the ratio of two functions, we can sort of introduce a new variable t. And then notice that dy dx is actually dy dt divided by dx dt. Well, again, it kind of seems like we can just cancel dt, which is not true. It's not canceling dt. This is due to the chain rule for differentiation, but it works nevertheless. So by doing this, we can from the original differential equation we can get this system of differential equations. Of course, such a system of differential equations is not really easier than the original differential equation. But what if g were a function of of just y, and f were a function of just x, right? So what if initially, if we didn't have this and we didn't have this, then which means the original ODE is separable, then what we get is something like this. Well, now, for the time being, you don't really have to understand it very deeply, and to process it is not really something new. But it is going to be important much later in the course, when we are going to apply this to solve certain systems of differential equations. But then, of course, I will remind you about how this is done.